Now, the RSA algorithm is pretty easy to understand. And the only problem with this, the only way to make the RSA a secure algorithm is to make all the numbers extremely big. Okay, so that's basically what we try to do to achieve this. Now, the first part of the RSA algorithm is the key generation. Okay, the key generation. So there are two keys, which basically represent two integers. One of the integer is e. Okay, I'm trying to circle this number. One of the integer is number e. The other one is e. Okay. Now, so how are we going to generate the keys? Okay. So we're going to actually talk about this in the next slide. Okay. Once we got the keys e and d, then the encryption is pretty simple. Okay. So the encryption going to be, so for the plain text, the original message, suppose we encoded the message into a number, a pretty big number. So that number is m. Okay. And then we, based on the number under the keys, so the plain text number m is the plain text, which is an integer. Okay. Now, E and D, I'm sorry, are two keys. One can be a public key, the other one can be a private key. And then we need to figure out another number n, also very large number, integer. Okay, we're going to talk about how to generate the number n. And based on the n, then we're going to generate E and D. Okay, now once we got these three numbers, E, D, and N, so E, D, and N are related. These numbers are related. So then once we got E, D, and N, then we can generate the ciphertext. We can encrypt the message. Okay, so let's say M is the original message, which is actually a number, an integer. So let's actually generate another integer, which is a ciphertext. Okay, here's what we do. So we're going to do m to the e. So that's the power. M to the power e. And then modular n. And then this generate a number c. And this calculation is relatively simple and easy, because even though the number m, the number e, the number n, they are huge number, but because we have a modular operation, remember, we can use some of the property of the modular operation, right? So we can easily, calculate these value and get the number c. The number c going to be smaller than n, and also number n should be smaller than n. Okay, and then once we got a c, okay, and the encryption using one of the key, which is e, right? And the decryption use the other key, which is d. So it's going to perform exactly the same operation. Okay, so once we got the ciphertext, so then we can calculate the c to the power d modular n. So then we will find out this will be the value m, which is the plain text. Okay, now you can understand. So we can generate m, and then for any actual plain text m, we can actually calculate the ciphertext. Okay. Let's see. So let's see. Actually, we can encrypt it. C is actually calculated this way. Now we can send this. We can send out the C. Okay. And also, if one of the key is public key, the other one is private key. So either E is a public key or D is a private key. Okay. Then we can actually use the other key to decipher it or to decrypt it, and we got M back. Okay. So that's the math behind these RSA algorithm. Now the idea is, if we know M, we know E, we know M and D, then it's easy, relatively easy and fast to calculate C. But when people doesn't know D, then it's difficult to find M, because so we only with the knowledge of C and N. So N could be also public, people should know M, N. But if they don't know D, so then they cannot find the M. Unless you know D, then you can calculate the, M by using the C to the power D modular N, which is relatively simple to calculate. And then we can easily get the things back. Okay. Now let's actually check out how this is going to work. Now the first step, okay. The first step is we have to make an assumption that it is possible to find a value E, D, which is, these are the keys, right? And the N, which is a big number, such that the MED modular N to the N equals M. Okay. For all M less than N. If we can do this, if we can find the ED and N such that this equation is true. That's one assumption. We can find these three numbers, ED and N. And also, it's relatively easy to calculate the M to the E modular N, or E and the C to the D modular N. It's relatively easy to calculate for any value M less than N. But it's infeasible to determine D given E and N. So that means if you actually publish E and N, so then you make E a public key, right? Then it's still not easy to find the private key. Now, if the public key E, now people can find out what the D is based on the public key, then there's no secret anymore, because then everyone can actually find the D, and then they can actually decrypt the message using this formula. So it should be very difficult for people to find the D, even if they know E and N. Okay, so that's the other requirement. And now we find out the RSA can pretty much achieve this for now. I just say for now, because with the power of the computer system now, it's basically infeasible. It's computationally infeasible to people to find D given E and N. Now let's first figure out how to set up the keys. Okay. Now the RSA algorithm is based on two prime numbers. Okay. So first we need to find the two prime numbers, P and Q. Okay. Now these P and the Q should be extremely large. Okay. And there should be different prime number. And then once you find these two prime number P and Q, you should keep these two numbers secret. You cannot tell everybody these two prime number. Okay. Now, how can I find a prime number? Then you can use remember the algorithm called Miller-Robbin algorithm, right? So you can actually randomly test a number, and if they, pass the Miller-Robbin algorithm for like 20 times, then this number is pretty much a prime number. If it failed, then you try another number. Failed, try another number until you find a number. And then once you got one prime number, then you can try another number, which is different, and using Miller-Robbin and test that number. Okay. So once we actually test these two numbers and find P and Q, okay, then the next thing we're going to do is you're going to actually do the multiplication. P times Q. Okay. Now P multiply Q, and you got the number N. Okay. So now you generate the number N. Now, the next thing, this is very important. That's the key for the RSA. Now, you're going to actually find out the Euler-Toltius function, phi of n. Okay. Now, what is the value of phi of n? Because n is the product, the multiplication of two prime number, p and q, right? Now remember, we have a formula. If p and q are prime numbers, then you can write this as p times phi of q. And p is a prime number, so phi of p is p minus 1, right? And the phi of q is q minus 1. So you can easily calculate phi of n, which is this number. And then once you find two prime number, p and q, then you just multiply p minus 1 and the q minus 1, and then you got a phi of n. And the n is p times q, and the phi of n is p minus 1 times q minus 1. Now, let me explain this. At this moment, we generated two prime number, p and q, and we multiply these two prime numbers, so you find the n. Now, and then with this n, so we can easily find the Euler-Toltius function, which is p minus 1 times q minus 1. Now, my claim is, if I keep this p and q secret, it's an extremely big, these are extremely big prime numbers. If I keep p and q secret, and then even I publish the number n, now people still cannot fact the number n. People still cannot fact the p and q. Now technically this is not right, because for any number, you can always factor the number. But what I'm trying to say is, even with the support of modern technology, using the fastest computer system, the most powerful computer in the world, and you try to write the algorithm, try to factor number of n, it's still going to take extremely long time to do that job. Now, how long this time going to be? Let's figure it out. Okay, we'll talk about this. You will not believe that. Okay. So that's the assumption. Now, if I build two large prime number, and I multiply these two prime numbers, and I got n, and even I publish this number of n, and I challenge people, say, could you please factor this number n? and find, and they cannot, technically they can, in theory they can, but it's computationally infeasible for them to factor the number. Okay, so we can assume that it's impossible to factor the number. Now, if they cannot factor the number, so then they don't know n is the multiplication of p and q. So they cannot, decide p and q. And so they cannot find the phi of n using that formula because they don't know p and q. So they cannot calculate the phi of n using this formula. Now, if they cannot find the phi of n using this formula p minus 1 times q minus 1, now what's the way to decide what's the phi of n? What's the definition of phi of n? Anyone recall this? The phi of n is defined as the number of integers less than n, the capital N, and also relatively prime to n, right?
Yes.
Yes. So now, what is phi of n? Because we know n is not a prime number. It's actually the multiplication of two prime numbers. So n itself is not a prime number. So you cannot say the phi of n is n minus 1. That's not true because that's only true for a prime number. So now you have to use the definition. So basically, what are you gonna do? You're gonna check whether 2 and n, 2 and n are relative prime, 3 and n are relative prime, 4 and n are relative prime, 5 and n are relative prime. So you need to check all the numbers from 2, 3, all the way to n minus 1, right? Make sure, which number is relative prime. And then you count the total number, and that's the phi of n. So it's the number of integers smaller than 2 to n minus 1. So these are number of integers smaller than n. So that's why it's 2 to the n minus 1. But relative prime to n. So that's the phi of n. Now, how much time people expect to do to find out this? So now, so that means you need to actually, for 2, you need to calculate the GCD 2 and n. So make sure it's 1. That means, okay, they are relative prime. And GCD of 3n, if this, so you need to find you need to calculate the GCD, for any of these number, and make sure that if it's relative prime, then you count this number. If they're not relative prime, you exclude that number. So then you got the total number. Okay, so that's the only way you can do it. But if you can factor this number, so which is actually the multiplication of two prime number, then you can easily calculate this. But otherwise, we assume calculating phi of n is also computationally infeasible if they don't know p and q. Okay, now we're going to analyze this also. Okay, later on, I will tell you why. So once you got a phi of n, then you can select a random number e. So make sure e is between 1 and a phi of n. E is between 1 and phi of n. And also make sure the greatest common divisor between e and a phi of e is 1. Okay. Then if that's the case, then we can say that's one of the key I find out. So I define this e one of the key. And now, how can I find the other key? The other key is, so I find the other key, which is E times D modular n is 1. Modular phi of n is 1. So that means E and D are basically inverse to each other and the modular phi of n. So that means E times D modular n or phi of n is 1. So this is the same as this. Okay. So you're going to find a D such that the E times D modular phi of n is 1. Now that's called the inverse of E and the modular phi of n. So now we find the D. Okay. Now if we know phi of n, then we can technically find the D easily. And then we find the two keys. One key, I can call this public key, I can call this private key. And the E and the N combined as a public key. D and N combined as a private key. Now, even if people know this, they still cannot figure out the D because they don't know phi of N, right? If they know phi of M and they know E, they know phi of M, so they can actually easily find the D. But if they don't know phi of N, so that's the key. So you keep the secret for this for the, make sure you don't tell people these two prime number, and make sure you don't tell people phi of n. Okay. Then you're safe. Even if you tell people what is the value of E and N, that's okay. You can tell people, say, this is my public key, and they cannot find the D and N. No, they cannot find out because to find the D, you also need a phi of M, but you have to keep this phi of M secret. Okay, so that's how you're going to create the two keys. Now, once you find the key, then you can use the algorithm. Okay, so you find the E is a public key and D is a private key. So now if you have a plain text M, so then you can calculate the ciphertext C by doing this, M to the E, which is the public key, and the modular N. So now here they use lowercase n, but in my case, I use capital N. It doesn't matter. So that's the N. Okay. Now the decryption going to be relatively easy. So once you got a C, but if you don't know D, then you cannot find the M because if D is not known, so you don't know how to calculate D, but calculate the M. But if you have the value of D, that's the private key. So now, so for example, if you generated these two keys, now if someone wants to send you a message M, so they can grab your public key and calculate the C, and they can send the C to you, and then you can decrypt the C by using your private key, C to the D modular N, and then you can restore the M. But the other people, they cannot, even though they get a C, but they still cannot get an M because they don't know D. And they also cannot find the D because it's difficult. So it's pretty simple, right? It's just that's just the that's how the RSA works. Yes.
In the previous slide, D is it's saying D is a different one, like D is equal to D minus 1 mod of phi of n. But before that, it was showing some different one.
In the previous one, this one, it says E times D equals 1 modular C of M. So B is not 1.
Oh, yeah. Okay.
So you can say D is actually E to the minus 1. That's the multiplicative inverse. But yes, you can write this. That's a notation. Okay. But when you say E times D equals 1 modular phi of M, then D is the inverse of E.
Okay.
Modular phi of M. So it's the same. So yeah. So yeah, this is almost same. This is the same as saying that the D times E modular phi of N or N, now it's lowercase n, equals 1. So this is the same. Okay, yeah, that's good. So it's not E minus 1, it's actually E to the minus 1. So that's So that's basically, we use the same notation, because in real number without modular operation, when you say x times y equals 1, then y is the inverse of x, right? Y is the multiplicative inverse of x. Is that right? So we use the same notation. Say d is a multiplicative inverse of e, but in this case, under modular phi of n. Okay. So it's not really the inverse. It's an inverse. It's a modular inverse. Okay. Any questions? Okay. Now let's take a look at the example. Very simple example. Okay. So now I'm going to be back with this one. This is actually tells you theoretically why RSA works. Okay. Why this is the case. Okay. Now, but before we do this, let's actually take a look at the example. So I pick a 2 prime number. P is 17, Q is 11. Okay. So I multiply P and Q. So I got an N. So P times Q, 17 times 11, that's 187. Okay. So I can calculate the phi of N by using this formula, which is P minus 1 times Q minus 1, which is 16. 17 minus 1 is 16. 11 minus 1 is 10. So it's 160. Okay. Now, this example, you can argue with me and say, well, I think people can factor that number, right? It's easy to factor 187. So you just divide 187 by 3, by 5, by 7, by 11. So you can just try all the possible division, and then you can find out, oh, I find out that, 187 can be divided by 11. So then I find the one factor, so I can find the other factor. Yes, that's easy to calculate. So I lied. So in this case, n is, once you publish the number n 187, people can figure out what are the factors. They can easily find the p and the q. Why? Because the prime numbers I give, 17 and 11, they are too small. They're too small. So they can actually even use computer program, just do the loop, right? So they can do the loop. Divide 187 by 3, divide 187 by 5, by 7, by 9, by 11. So you can always divide a number, and then you can always find a number which can divide 187. And it's very quick. Okay. So no wonder. So that's not, so this number is not secure. No one gonna use this two prime number. Okay. So now I assume that once I publish 187, people cannot figure out how to factor it, because n is too big. 187 is too big. So they can calculate the phi of n. So now if they want to if they cannot factor n, so when they try to figure out what is phi of n, so they need to figure out 2, 3, 4, 5 for each of the number all the way to 186. You need to figure out whether this number is relative prime to 187. This number is relative prime to 187. And then you can find out all the numbers that are relative prime to 187. And then you can find the phi of n, right? Which is 160. Okay. And then I can select the E, make sure that the E is relative prime to phi of n, which is 160. So then I pick a E equals 7. So I can pick any other E. Okay. Now, the next step is a relatively tricky, but it's actually it's doable. So you can find the D, determine D, such that D times E equals 1 modular 160. And the D should be less than 160. Then I find the D equals 23. Don't ask me how I get this number, but we can verify, right? So 23 times 7, what is number? 23, 7. So 161, right? So 161 modular 160. 161 modular 160, that's 1, right? So that's why once I given 7, 23 is a inverse of 7 modular 160. Okay, so 23 times 7 equals 161, which is this. So they're related. So these two numbers are inverse to each other. Under modular 160. Okay. So I just released the public key, which is 7 and the 187. Don't tell people this 160 because it's going to take a while for people to figure out what is phi of n, which is 160. And then your private key, secret key is 23, the other value, and the 187. Okay, now to do the encryption, so then you can actually encrypt a number. So for example, if the plain text is 88, which is smaller than 187, right? So you have to make sure the plain text you choose must be smaller than 187, the value n. Okay. So now, so when you try to figure out what's the encrypted message, then you say 88, that's a plain text, to the 7, that's public key, right? 7 is the public key. To the 7. Modular 187, and you got 11. So now you can send 11 to the destination, say that's a ciphertext. Okay. Now, on the destination, with the ciphertext 11, then you can use the private key, which is 27 or 23, right? The private key is 23. You can 11 to the 23 modular 187. Then you will find out it's 88. So that's the plain text. So you can actually encrypt the message. You can decrypt the message. Yeah. That's RSA.
If we know the n value, isn't it easy to find phi of n? Because n is a multiplication of two prime numbers. So if we know the n, so we'll definitely know what are the
If you
prime
know
numbers.
if you know n, in theory you can find out the two factors, right?
Yes.
But I will find out why it's technically infeasible. Why? If I given n, if I find out a prime number which is extremely big, then you cannot. Okay. Now here's another example. I hope you can see that number clearly. So suppose this. I want to send a message. Say, how are you? Okay. So now I can encrypt the message how, HOW, and I use the ASCII code. So H can be 33, O could be 14, W could be 22. So then you can actually encrypt the message like this. Okay. Now, what are you going to do is you can, let's see. You can actually use two prime numbers. Now, one of the prime numbers P is 73. The other number, prime number Q, is 151. Okay. So now, what is N? N is P times Q, right? So this is N. So this is N. So it's once you find a P, once you find a Q, and then you multiply P and a Q, and then you find the N. Okay. So that's N. So now you can find the phi of N. The phi of N is pretty easy to find, right? So phi of N is this 73 minus 1 times 151 minus 1. So that's 10,800. Okay. And then the n is this. N is this. Phi of n is this. Okay. Now, if I pick a e equals 11, I can easily, not easily, but there must be a formula. You can find out the inverse of e and the modular phi of n, which is 10,011, is 5,891. So then you find out e is 11 and the d is 5,091. So the public key is 11 11023, right? That's public key. Private key is 5891 11023. So that's n. That's this. This n. And this is public key, which is the e. E is relative prime to this phi of n. So d is actually, so e times d modular phi of n is 1. Okay. So now I can find out, okay, so d is this. Okay. D is 5,891. So now if n is this number, so I can actually, for this long number, I can combine these first two numbers. So 3314. So that's basically the first two HO, right? And the second one, 2262. So that's P2. Okay. Now P3 is 00117. So I combine every two numbers and I just make it, and then 0462, 0462, 2414, 2414, and 2066. So basically I can split these into 1, 2, 3, 4, 5, 6, 6 numbers. And these 6 numbers are all smaller than n because they are 4 digitals. N is 5 digitals, right? So I can make P as a plain text, P2 as a plain text. So then with P, I can P1, which is 3314. I can actually, 3314 to the 11. This is the public key. Make sure modular n. This is private. No, this is C1. And then I can calculate C2, C3, C4, C5, C6. So C1 is corresponding to P1, C2 is corresponding to P2, C3 is corresponding to P3. Okay, so I got this. Now to decrypt the message, then you need to actually say C1 to the 5,891 modular n, which is 11,023. So actually, this is actually a huge operation, right? So you need to calculate the 10,260 to the power of 5,891. Technically, this is a huge number. But you think it's a huge number, but for the computer, it's not that huge. So you can still actually, so this algorithm is still not safe because P and Q are still small because P is 73, Q is 151. These two numbers are too small. Okay. But this basically gave you the idea how I gotta encrypt the message. Okay. How can I generate the two keys? So I first find the two prime numbers, and then I multiply these two numbers, and I create a number n. So number n, okay. So n is P times Q. And then I find the phi of n. And then I find one of the key, which is relative prime to phi of n. And then I find the D, which is multiplicative inverse of E, modular phi of n. And then I use one E as the public key, D as a private key. Actually, it's the combination. The E plus the N is the public key, and the D plus the N is private key. So N is not a secret number. So people know N. But for this number, if you got the N, which is 11,023, I think without the help of computer, 11,023 is actually very difficult to factor, right? But with the computer, it's still not that difficult because it's only 11,023. So you can actually divide it by 3, divided by 5, divided by 7 and 9. So you can actually do the loop and you can find the factors. So eventually you're going to find out, 73 can divide the number. So you can find a 73. Okay. Now, the question is still, how can you claim this algorithm is safe? Because it looks like if I give you two prime numbers, you can always factor the number, right? Once you multiply these two prime number, get an n, you can always factor n. Okay, now let's take a look at this example. Okay, let's take a look at this example. Now this is actually the actual number you're going to actually use. Suppose P is this number. How many digitals? You can count it. I think it's probably like a 150 digitals. 150 digitals. 100 digital digits. And the Q is this number. Okay. Q is P and a Q. They're different. Okay. So the first three are the same, but fourth one is different. So I tell you these are two prime number because I tested these two numbers, P and Q, using Miller-Rabin. Now you have an idea what kind of number RSA going to use. RSA going to use a huge number. I'm not kidding. Now this number, these two numbers, what do you think? Are they huge?
Yeah. Okay.
Yeah, they're huge. But in modern days, they're not really that huge because now in modern days, because the computer becomes more powerful, so people actually now start to use the RSA with the numbers of like between 200 digits and 300 digits, between 200 and 300 digits. It's longer than this number. Okay. Now, looks like people are going to continue to increase the actual number of digits because as the computer becomes more and more powerful. Okay. Now, what is the value n? N is P times Q, right? Okay. So we calculate the n, which is P times Q, and this is n. Okay. Now you're probably going to say you're lying because how should I know this is correct, right? I swear this is correct. Okay. And then what is phi of n? Phi of n is a p minus 1 times q minus 1. And then p minus 1 times q minus 1. And this is phi of n. This is n. This is phi of n. Okay. And then we pick number, randomly pick a number e. Okay, so that's the e, which is relatively small compared with the other number, right? So then I just randomly pick a e, And we tested that the GCD of E and phi is 1. Okay, so then I can use E and N as one of the key. Now, what is D? How can I find the D? And D is this number. That's a huge number. So E times D modular. Oh, I'm sorry. B of N. Okay, not N. Is 1. So that's D. So now I got the E of E and N, that's public key, and the DN, that's private key. Okay, so then I can pick any number which is smaller than N, which is smaller than this N, then I can encrypt that number. Okay. So then I pick a plain text M, right? So I multiply M to the E modular N. So M is this number, E is this number, okay? And modular N is this number, right? So I got the ciphertext. See, this is a ciphertext. Okay. Now to decrypt the message, decrypt the C. So all I need to do is M. So C to the D. Actually, that's power D. Okay. C to the D modular N. Now this is actually tough job, I tell you. Why? Because C is huge, right? C is this. Let me see. What is C? Oh, this is C. Okay, so that's a huge number. And then C to the D. What is D? This is D. Now, what is C to the D? Modular N. Now we find out I'm pretty sure that's this number. Okay. Are you excited? Okay. So that's the real RSA algorithm. Okay. Now let's actually, so I have a program, computer program, so I can use. Now, if you actually know the language of Java, there is a class called big integer. Okay, so this class big integer can be used to perform these operations, because you cannot just use the type like int, because the int only can store 32 bits. So the largest number it can represent is pretty small. It's almost nothing. Okay. And also, if you want to just calculate this, you can actually just check the big integer. Let me actually show you what I have now. So let's see. Okay. So I'm not going to ask you to do this, but if you want to, know about this big integer, then now this is actually the Java code I have. So I use the class called the big example. So I use the class called the big integer. So I can declare P, Q, and N. So for example, I defined P as an integer. So this is a P. Okay. That's a number P. And that's a Q. Okay. Now, to perform the operation, when I actually do the operation like a P plus Q, I cannot say P plus Q. Okay, I cannot simply say P plus Q. That's not going to work. So when you do the P plus Q, then I'm going to actually, so I pick a number P, and then I use a formula, which P is a big integer. Big integer has a method called it's probable prime. So I test it 10 times. So then if P actually, if I pass it, then it's going to print out to say P is most likely a prime. And if P is Q is a probably prime, so if pass it, and the Q is probably a prime. So that's basically what I do. Now, when I do P times Q, then I'm gonna say P dot multiply Q. So that's N. So P times Q. So these are the, because you treat the big integer as a class. So it's a class. P, Q, N is a big integer. It's a class, but it has a value. So the value is like this. Okay. So now let's test. Just do a small testing. Okay. Let me actually do this. Um, um, so you don't have to. So let's see. I can compile the Java C, big example. Okay, so I compile it. Okay, so then I can run this program. Okay, so this is a mess. Okay. Yeah, so this number is most likely a prime. So the number I just imported is most likely a prime. And this number, it's too long, so I cannot represent using one line. This number is most likely a prime. So I can use this two number as a prime number. So if you feel like this is not safe, I can just using mirror lobbing and I try 20 times. Okay. If actually mirror lobbing successful in 20 times, then you can pretty much say it's almost like definitely it's a prime number, even though it's still statistically it's a prime number. So yeah, it's like most likely a prime. It's most likely a prime. So once you got these two number n, p and a q, and I calculate the n, okay. So that's the number of n. Now, can you factor this n? Can you factor this in? Okay. Now let's do a small math, and then you can find a phi of n. Okay. So the inside between two parentheses, that's n. Phi of n is this number. Okay. And then I pick a e, is qualified as a key, and d is this. Okay. Now for plain text n, the ciphertext c equals n to the e modulo n, which is this. And the plain text after decryption is m equals this, which is the same as this. Okay. So if you try to check another number, so I can pick another number n. So let's say, please complete the following computer. Let's say, okay, for plain text n like this, right? So I can increase the number of n to this. Okay. Okay. So I increase the number. Okay. So then what is C of n? And what is, so let's just save it. Okay. So if the number m is this number, then the ciphertext C is this. And if I actually do the decryption, I got m back. So that's the C. So this is C, and this is M. This is the same as this. Okay. So you can now I just give you some sense how the RSA gonna work. So RSA gonna work on extremely big number. Now let's do a simple math before I call it a day. Okay. Now how should I know it's kind of safe? Okay, let's do this. Okay. Let's do this. Now suppose P is a prime number. Now P it has P. Oh, sorry. If P is a prime number of, let's say, 150 digits. Okay. Q is a prime number. It's also about 150 digits. So P is about in the neighborhood of like a 10 to the 150, right? If it's 150 digitals. So for example, if the P is actually like a 5 digitals, like a 1, 2, 3, 4, 5, and then I can write the P as 1.2345 times 10 to the 5, right? Or 10 to the 4. 10 to the 4. So then you can say it's 149. Okay. Now Q is about 149. So what is that? How many digitals n gonna expect to have? N is a P times Q. So how big is the n? So P is some number like a single digital number, right? Single digital number. Let's say x times Q is a single digit number, y times 10 to the 149. So x and y are single digit, right?
298.
It's like a x times y times 10 to the 298. So n has pretty much like a 299 digits, right? Now, if I try to actually test if I try to find a factor for n, so if I use a traditional way, like I use a loop, so I can divide n, because P is a prime number, so it's an odd number. Q is an odd number. P times Q are odd number, right? So n is odd number. So then I can just say, I can divide n by, n can be divided by 3, 5, all the way to, I think, half of n, right? Pretty much 3, 5. I just divided all the odd number. Okay, half of n. Okay. So how many loops I expect to have? So if I actually divide like 3, 5, 7, 11, I just use all odd number, so I can actually all the way go to n minus 2, right? So that's almost like half of n. Now, then if I actually choose 3 to n, I cut it into half. From 3 to n minus 2, I cut it into half, just 3 to like half of n. Half of this. So it's almost like a half n over 4, right? So I'm going to do the loop of n over 4. So what is the n? N is 10 to the 298. And now divided by 4. So I'm going to do the loop. I'm going to loop like 10 to the 298 divided by 4. So let's say it's 10 to the 297, right? Because divided by 4, even I divide by 10, it's actually 10 to the 297. So it's actually, this is definitely bigger than this, right? So I could just do this. Now, when I do the loop, that's 10 to the 297. So I'm going to do that many loop when I do using the computer. Now, suppose my computer is powerful, so I can perform. So I'm going to check 10 to the 297 times for each of the number. Okay. So you're going to do division, right? Divide actually that n by 3, divide n by 5, divide n by 7 to see whether I can completely divide it. If I can completely divide it, I find the factors. Okay. So I have to try this many times. Okay. So now when I try this number of loops, so suppose my computer is powerful, I can do 1 billion division in a second. I can do 1 billion division in a second. Okay. 1 billion division in a second. So that's pretty powerful, right? So it's a 10 to the 290, 10 to the 297. So if I do the division, I can do 1 billion. Okay, divisions per second. Okay. So 1 billion is what? 1 billion is a 10 to the 9th, right?
9th.
Yeah. So every second I can do 10 to the 9th division. Now these are the total number of division I need to do. So that means how many seconds do I need to complete all these division? The number of seconds. So it's a 10 to the 297 divided by 10 to the 9. So that's the number of division I can do for per second. That's the total division I need to make. So this divided by this, so I got a 10 to the 288, right? So that's the total number of seconds I need. Okay, seconds. So I need to actually run this operation on my computer 10 to the 288 seconds. Okay. Now what does this mean? 10 to the 28 second. 288 seconds. So if I divide this number by 60, I get a minutes, right? So that's the total number of minutes. And so if I divide by 60 again, so what's this number? That's the total number of hours I need to spend to do this loop, right? And then divided by 24, that's about how many days, number of days I need to spend. And then divided by 360, that's the number of years I need to spend. Okay. Now what is this? What is this number? 60 times 60, that's 300, 3,600, right? 3,600 times 3,600 times this times 24. So what do you get? Okay.
About 31 million.
31 million. Okay. Let's say 100 million. Okay. Let's just say 100 million. Okay. The total is 100 million. So 100 million is 10 to the 8, right? That's this. Okay. 10 to the 288. So that's 10 to the 280. 10 to the 280 years. Okay. So if I try to factor this number, a number which is actually about 300 digitals, like a 298 digitals. If I want to factor this number using the computer algorithm, with the computer that can perform 10 to the 1 billion divisions per second, it requires 10 to the 280 years. Okay. Now in theory, in math, it's always possible, but practically.
Just lost your audio.
Okay, you lost my audio? Okay. I don't know why my audio is lost. Can you hear me now?
We can hear you, Professor.
Okay. So you need to check. You need to check your. Okay. So 10 to the 280 years. Okay. Now, what's the life for our Earth? The Earth is actually, I think it's 140 billion years, right? 140 billion years. Okay. 140 billion years. What is this? Okay. So 1 billion is 10 to the 9. And 140 billion. So that's less than 140. That's 1.4 times 10 to the 11. So that's the life of, that's the life of our Earth, So basically, so that means if you start to actually compute this factoring problem, it's not going to work. It's much longer than the life of Earth. So that's basically tells you what does it mean. Okay, so if I choose any number which is like a 150 digits and another 100 digits, and multiply these two numbers, and if I got n, if I publish this n and ask people, challenge people, say, can you factor this number? And the chances are that's practically impossible. Technically, it's impossible to factor this number. So that's the reality, because now the previous example we use, like we use 17, we use 23. These numbers are so small that people can easily actually factor them. Okay, 17 times 23. That's easy job to find the factor. But if I give you these two numbers, P and Q, okay, if I give you these two numbers, and then then I multiply these two numbers, ask people to factor this number. Now it's technically impossible to do so. Okay, that's what I mean. It's impossible. However, doing this modular operation, it is possible, because with the modular operation, I can use the trick we did, right? Use the approach like so it's still a lot of work, but it's not impossible. It's very quick to calculate. because you can check my Java code with big integer. So when you do actually like when you got E and a D, right? Okay, so when you have a M, so M to the E modular N. So what you're gonna do is you can actually do this M to the E modular M. Then M is smaller than N, so then you can multiply N to the E. Then you can use M square, E divided by 2 modular N. So you can use all this trick to, M square. If M square is still less than N, so then you can use N to the 4th, then E divided by 4. Something similar trick like this. Then you can actually relatively easy to calculate the, because the M to the E is M mod N to the E mod N, right? So that's the formula you're going to use. Okay. So I think I don't want to actually talk anymore. So if you look at the PowerPoint presentation, I actually introduced another algorithm. It's called the Diffie-Hellman. But Diffie-Hellman algorithm is simpler than the RSA. So if you're interested in, you can take a look. But if you're also interested in, you can even actually talk to me, so I can show you how to do this, RSA algorithm. You can use the big integer in Java. Okay, the bigger integer. If you use the bigger integer, you can easily check it out. How to, there's, if you actually search Java, say Java, use Java big integer. Okay. Let me show you what it is. So if you search the Google, say class big integer in Java, so you will find a lots of different methods. Okay. So you can actually find the GCD, the greatest common divisor between two numbers. You can call method to calculate this number, and you can get the lowest, and then you can actually use the modular operation. Okay, you can perform a lot of different operation, and this probable prime is a method that you can use to find out what is the, whether a number is a prime number. So there are lots of different methods you can use with big integer, and then you can deal with extremely huge number. Okay, so that's basically what we do. Okay, I think that's pretty much all I want. So if you want, you can check the class note, the handout for module 10. So you can skip the Diffie-Hellman part. You can just look at the RSA part, and if you can, try to do the homework assignment for the last one. So I apologize that we actually missed a couple of actually Wednesdays, so that's why I actually missed one of the module. But otherwise, I pretty much cover all the materials we're supposed to cover. I think that's pretty much it. So you can try the assignment 9, okay? So but for assignment 9, you can skip the second problem. So because I did not cover the second problem using Diffie-Hellman, but you can actually try the first problem, okay? So you can try the assignment 9 problem 1. There are a couple of smaller problems that you can actually practice. Okay. Okay, I think that's all. That's the last class for today, for the whole semester. So I think I checked all the homework assignment, the test. I think you all have did a great job. So I appreciate. This semester is really a challenging semester because we cannot go to the campus. So but you did a good job. So please check the assignment 9. Try to do the first problem because you can skip the second problem, as I say. And so tomorrow, in tomorrow's test, I'm not gonna actually include today's material, so you can skip today's material. Okay. Any questions?
Is tomorrow test gonna be 12 hours window?
You mean the
I mean,
test?
the earlier test it was 3 hours window, right? So does it? I mean, tomorrow test you said it's 12 hours window.
Yes. Check the announcement. I think I just make it clear. So you can actually let me show you. This is what I announced on the blackboard. Let's see what's on the blackboard. Okay. Let me actually first stop the recording for now.